podcast is brought to you by LMU Munich.
Thanks a lot. Thanks to the organizers for the invitation. That's very kind. And thank you to you all for coming early in the morning. So I will give some update on the string phenomenology, essentially emphasizing the topics that have been more active from my point of view in the last year or couple of years. So string theory has suffered along its history several phase transitions. At the beginning, in the early and obscure days, there was the idea of formulating the theory. Later on came the superstring revolution, and that took almost a decade to be developed. And in the 90s, there was some great insights into a non-perturbative string theory. Since the year 2000, I think the phase transition has been towards a decade, which is kind of longish, of applications of string theory. And there is a landscape of applications of string theory into diverse aspects related to the real world, like application to understanding black hole physics, ADS-QCD, inflation, condensed matter, and the particle physics models corner, which in a sense was with us since the 80s already. So in this talk, I will zoom into this particle physics model building, which is what's usually called string phenomenology. So the aim of string phenomenology is to realize the old dream that the string theory describes gravitational and gauge interactions in a unified framework consistent at the quantum level. Now, of course, we would like to realize a particular set of gauge interactions, namely the standard model, or some clever extension of it, which eventually will be realized at the TeV scale. So the avenue that the string phenomenology more or less takes is first to understand the basic mechanisms that realize interesting properties of this gauge sector, the standard model, like chirality, supersymmetry, if we are interested in supersymmetric extensions, gauge symmetry, modular stabilization, family replication, potentials which are flat enough to develop inflation, instantons, many things. And then determine classes of constructions which incorporate subsets of these. Of course, the final aim would be to incorporate all of them all together, but that's too hard for the moment. So at the moment, we're just happy with incorporating several of them. So typically, we look for classes realizing non-abelian gauge interactions, replicated charge fermions, Higgs scalars with Yukawa operators coupling to the chiral fermions, and then try to incorporate modular stabilization, perhaps tuning of the cosmological constant, etc., etc. And within each such class of models, you try to obtain models which are as close to the standard model as possible. It's a very old program, but it has been progressing substantially, essentially following many formal developments which have been applied to developing these things. Happily, I think that we're getting to the point where there will be some data-driven area, and the activity in the field will be forced by data, like the recent discovery of the Higgs. And in fact, it has already started, so I will comment on that towards the end. So to this, to apply or to obtain these string phenomenological models, there is a landscape of possibilities on how to do that. There are many constructions which, of course, are related by different dualities, which are devised to engineer these standard model-like properties in string theory. For instance, putting d-branes at singularities, or considering intersecting brane models, magnetizing branes, heterotic models which are with us since the 80s, and then models which are more based on geometrical properties of compactification, in particular on singularities like M-theory on G2 manifolds and F-theory on fourfolds. Something which is remarkable about these constructions, and which is often not perhaps emphasized, in particular not by me, but I will do it today, is that the generic four-dimensional compactification in string theory is chiral. So very often it's emphasized that it's very hard to get chirality from d-branes, etc., but that's not really correct. That's correct only from our limited human point of view, where simple d-brane configurations are just parallel d-branes or overlapping d-branes sitting at smooth points in flat space or something like that, and that preserves too much supersymmetry. What is really generic in string theory is that branes are wrapped in complicated ways, and whenever they interact with each other, they develop chirality. So similar for compactifications of M-theory or M-theory or F-theory, you compactify on the most general G2 or Calabi-Yau fourfold, and in general you will have singularities that correspond to existence of chirality. So it is remarkable that the generic four-dimensional compactification in string theory develops chirality in a natural way. So I will overview some of these constructions with an eye on recent developments. Let me just apologize because the discussion will necessarily be incomplete, and there are many interesting works that I will not be able to review or discuss. And I will also follow a particular path. So these constructions don't form an ordered set, and there are a lot of interconnections, so I will just pick a particular outline. So the introduction I already gave. I will start with the discussion of D-brain models, move towards F-theory developments, and then later on move towards modular stabilization and influxes, a little bit of de Sitter, and only towards the end I will just move to heterotic models, although they are the oldest. And then, time permitting, I will move towards some little discussion of the Higgs. So let me start with a prototypical class of models which realizes the standard model or something close to it in string theory. It's kind of a standard to start with the heterotic, but let me be provocative or innovative and start with intersecting type 2A D6 brain models. And the reason is that they are very geometric and they exemplify many of the properties which come up in other setups later on. So I will use this class of models to illustrate a few points that appear in model building. So the starting point is to consider type 2A string theory compactified on a Calabi-Yau with some orientifold action so that you preserve at most n equal 1 supersymmetry. You could also break to n equals 0. And to add orientifold 6 branes because of these orientifolds and these 6 branes. And these 6 branes you add in a pretty generic fashion. I mean, they will be wrapping 3 cycles in the internal Calabi-Yau space in this particular way. If you're interested in supersymmetry, which one usually is, there are supersymmetric conditions on these 3 cycles pi for the branes to preserve some common supersymmetry. The cycles must be a special Lagrangian. So there are 2 conditions which, from the point of view of 4 dimensions, they correspond to some F-term condition and that depends on the Keller moduli, and a G-term condition that depends on the complex structure moduli. This special Lagrangian condition is a slightly more restrictive version of what people in topological strings call A branes. And in a sense, these are like pretty generic branes that one can use in compactification. So these kind of conditions essentially mean that your branes are only supersymmetric in a particular locus in moduli space. And later on we will see in heterotic that this has been used, something analogous to this has been used to argue that there is modular stabilization in particular setups. And I think Lara Anderson will be discussing about that. So since these branes are pretty generic in the sense that I was mentioning before, when you compute the open string spectrum, open strings stretching among the different branes, they develop chirality. And the chiral sector is very special, it is protected, and it is given by topological properties of the compactification and the branes. So in particular, the gauge group is just given by a product of unitary factors with ranks given by the number of branes in each brane stack. Of course, there could be other, because of the orientifold, there could be other SO and SP groups, but let me just skip their discussion. And then there are chiral multiplets coming from open strings stretching from branes A to branes B, which are in this kind of bifundamental representations with some multiplicity, which is given by the intersection number of the 2 cycles which are intersected. So it's a topological origin of family replication, and the fact that the net chirality of a model is topological is something expected on 4-dimensional grounds, and it's something that, because of that reason, appears everywhere in string compactifications. This topological replication could take the form of intersection numbers in this setup, or typically the index of some Dirac operator in heterotic compactifications or in F-theory models, etc. So with these model building rules, which were essentially proposed in the early 2000s, people try to construct things close to the standard model or the MSSM, and there are these diagrams which are called the quivers or something like that. They are analogous to quiver diagrams, in which you just propose which set of branes you have and which intersections you propose to reproduce in the chiral spectrum. Now, very often these models contain chiral exotics, which is not a good thing to have to do model building, but they can be avoided, and there is a lot of technology developed. And let me just emphasize the work of Gaby Honecker, who developed a lot of different models in different toroidal orbifolds and orientifolds to really find models without chiral exotics. And in fact, there are classes of theories that reproduce the MSSM without chiral exotics. Of course, they may have, or they have in general, non-chiral ones, but this will typically get masses from other processes and are perhaps something one should not worry about. Okay, because these theories are chiral, of course there are some consistency conditions that guarantee that the theory is anomaly-free. These consistency conditions are the so-called Ramon-Ramon-Tadbor cancellation conditions, which require that the total D6 brane charge must be equal to 0. There are also some K-theory charge cancellation conditions, which come in situations where the D brane charge is not computed just by homology, but rather by K-theory, but let me just simplify for the sake of the discussion. These consistency conditions are under constraining. So even though you do have some constraints, still there are plenty of models, and this is what some people call the flavor landscape of these theories. Now, these consistency conditions are there essentially to guarantee that the four-dimensional theory will have anomaly cancellation. For the non-abelian gauge symmetries, the cancellation is automatic, and for the U-ones, it requires some Green-Schwarz mechanism where the triangle mixed U1 non-abelian anomalies and also gravitational are cancelled by this kind of exchange where the U1 is coupling to some, in this case, Ramon-Ramon 2 form, and the dual of this 2 form, which is a scalar, is some kind of action which couples to two non-abelian gauge bosons in this way. So these diagrams can be computed and beautifully cancel the anomaly thanks to these Ramon-Ramon tadpole conditions, if you wish. Now, the existence of these linear couplings between U1s and Ramon-Ramon forms is very relevant, in particular to discuss the fate of the U1s that come together with all these unitary factors in here. So every non-abelian factor comes with a U1 free for the ride, and it's an important issue to discuss what happens with them. So essentially, there are these BF terms in here which give masses to all the anomalous, in quotations because there are no real anomalies here, to all the anomalous and some of the non-anomalous U1s. Essentially, you can trade this BF coupling to some kind of Higgs-like mechanism in which the scalar is eaten up. The longitudinal component of the massive gauge boson is the scalar dual to this 2 form. Now, because U1s tend to be generically massive, there are some important issues in model building. First, you have to require in your model that hypercharge remains massless. So that's not something automatic, but something that you have to impose and build a model such that it is like that. And this issue is very similar to the ones that appears in a theory when you try to make hypercharge massless by avoiding this kind of BF couplings, and I guess there will be some discussion about that. For the U1s, which are indeed massive because they are beyond the standard model and you're not interested in them, etc., still they remain as perturbatively exact global symmetries, so it's something that one should keep track of. Because you have these BF couplings in supersymmetric theories, there is a superpartner of this coupling, which is a field-dependent phi Diropoulos term, which essentially amounts or is proportional to the deviation of your brane system from the special Lagrangian condition. So it's a D term, because we saw that the special Lagrangian condition involved a D term condition. And although these U1s are perturbatively exact, there are no global symmetries in theories of quantum gravity, so at least in string theory. So there is a non-perturbative violation of these U1s, which in the present setup is coming from D-brane instantons. Nevertheless, these U1s, although they are broken, they can have some discrete symmetry group remnants, and although I will not discuss them today, let me just point out that this is something that I have been working on in the last couple of years. Okay, so far so good for these type 2A models. Many of these properties come in one way or another in other setups. Let me move towards type 2B models because they are perhaps more connected to other recent developments. By the way, before going to type 2B models, let me mention that all this perturbative discussion of the U1s is perturbative in the context of type 2A, but perhaps could be carried out more nicely if you lift these configurations of these experiments to M theory. What you'd have is compactifications of M theory on a G2 manifold or something like that. And these U1s would be, in a sense, absent in this geometric realization because their presence is, in a sense, an accident of perturbation theory. So probably there is a very nice discussion of U1s in these G2 manifolds, although the construction of G2 manifolds is a very hard topic, and there has not been many developments in that direction. On the other hand, in the context of F theory, there is a beautiful discussion of U1s that will come later on, which again is based on the fact that these U1s are a perturbative accident in a sense, but they can be kind of tracked in these non-perturbative F theory formulations as well. So let me move towards these type 2B models. There are many motivations to look at these type 2B models. First formal motivation is that they are mirror to the earlier type 2A models by the same mirror symmetry that relates type 2A and type 2B on Calabi-Yau spaces. There is an extension of that in the presence of branes and orientifold planes, so it is natural to think about what would be the generalization or how mirror symmetry works in the presence of these defects. So essentially what you obtain is type 2B compactified on Calabi-Yau orientifolds with B branes, which are just the mirrors of the A branes. That's a formal motivation. There are other more phenomenological motivations. Like for instance, in type 2b, it is much easier to carry out the discussion of moduli stabilization with free-form fluxes, and I will turn to that later on. Let me for a moment stop a little bit to think about what are these B branes. The B branes don't have such a simple definition as the A branes. You cannot just describe them as some branes wrap on some cycles, etc., etc., essentially because the concept of B brane suffers from alpha prime corrections. And in particular, there are two regimes in which they are controllable and they can be given a concrete definition. The first situation where one can talk about B branes in a precise way is to consider Calabi-Yauss with orbifold singularities or other singularities, and locating D branes sitting at such singular points. So a typical example is D3 branes at orbifold singularities or toric singularities. In that situation, the physics of the D branes is encoded in some quiver diagrams, and essentially the B branes are just representations of these quiver diagrams, or the category of representations of these quiver diagrams. So without going into such detail, let me just emphasize that the systems of D3 branes at toric singularities can be studied with some detail using the so-called dimer diagrams or brane tilings, to which Ami Hanani has contributed so much. And there were, even before that, there were some early local model building attempts in the sense of locating D3 branes at some particular singularities and getting some chiral theory localized on their world volume, and you can try to do model building with that. So there were some early attempts in the early 2000s by myself and collaborators, also Berenstein collaborators and Berlin Reinhold. Now, there has been some activity into these systems of branes at singularities, not in developing the local models, but rather into embedding them into global setups. In 2000, there were some attempts by Berlinde, Weinhold, Morrison and collaborators, and very recently, Fernando Quevedo and collaborators tried to engineer Calabi-Yauss where you could have appropriate singularities to obtain something like the standard model, and then have additional ingredients like modular stabilization in the large volume scenario and things like that. That's the first setup where B branes are controllable, let's say. The second situation is in the large volume regime, where the branes are actually geometric branes, and you can think about them as branes wrapping holomorphic cycles and carrying holomorphic and stable bundles. So the SUSY conditions, again, have some F-term condition, which is that the bundle is holomorphic, and they have some D-term condition, which is this stability condition. So in the way I wrote it, which is kind of formal, it's called a pi stability, and the point is that it involves a lot of alpha prime corrections. So typically this is controllable and can be understood at a large volume, where this condition essentially reproduces the Donaldson-Uhlenbeck-Yau equations, and you recover the stability. The pi stability condition becomes the slope stability condition of mathematicians, and I guess there will be some discussion of this by Lara Anderson, because it's this kind of definition of bundles appears naturally in the heterotic compactifications on Calabi-Yau spaces. So these branes are often also called magnetized branes, in particular in the toroidal setup, although one can define them in general Calabi-Yaus. And again, they lead to naturally to chirality, so they are very generic branes, and they lead to chirality in the sense I was describing at the beginning, and they lead to family replication. So the replication in this case is again topological, but it's coming from the index of the Dirac operator, which counts the number of Landau ground states in your particles moving in magnetic fields in this bundle, let's say. Okay. There is a very nice setup in the type 2B context, which is pretty much related to a theory, and part of this talk will be discussing the relation between F theory and type 2B. So let me just emphasize that there is a class of type 2B models which involves, in the large volume regime, these 7 branes wrapping on 4 cycles, so it is these large volume B branes. So essentially what you have is these 7 branes wrapping holomorphic 4 cycles and possibly carrying holomorphic gauge bundles, and they are responsible for reproducing the gauge group, which is therefore localized on a 4 cycle. The intersections of the 7 branes lie on 2 cycles, and they are responsible for the appearance of matter. There is matter at the intersections, and these are essentially the matter curves that appear in the theory. And finally, the triple intersection points of different matter curves are the situations where the Yukawa couplings are localized. So one problem of these perturbative models in type 2B with D branes is related to the U ones that I was mentioning before. So imagine that you want to find a model where you have natural unification. So something that I didn't mention is that in these models with different set of branes giving rise to the different gauge factors, it is not completely natural to have unification of couplings, because each gauge factor of the standard model will come from a different brane, which has a different gauge coupling. So the simple possibility to try to understand unification would be to consider a single stack of brains reproducing SU5 in higher dimensions, so it's an underlying SU5, not a 4-dimensional SU5. Now, in that situation, if you are in these deep brain models, the top Yukawa coupling, which is the coupling of, or coming from the coupling of 10, 10, and 5, is forbidden by the perturbative U1s that I was mentioning before. So the charges that you get naturally from open strings stretching between brains don't match for this kind of couplings. So again, these U1s will be massive, but they will remain perturbatively as global symmetries, and they will continue forbidding this top Yukawa coupling to all orders in perturbation theory. So the only way out is to go non-perturbative. There are several ways to do that. One of them is to consider instantons that violate this U1 and are able to restore, let's say, this top Yukawa coupling. This can be achieved considering D3 brains, Euclidean D3 brains wrapping 4 cycles. And the challenge there, in a sense, is to explain why these instantons, which are wrapping cycles, which in general could be expected to be large, are actually not suppressed. So you have to go to a particular corner in moduli space where these cycles are small, such that these instantons are not suppressed and can give rise to some order 1 top Yukawa coupling. Another possibility to go non-perturbative is to go to F-theory, where there is a natural non-perturbative built-in mechanism, which is this E6 point that will be discussed probably by Heckman, which is able to yield or to produce this order 1 Yukawa coupling. So the picture is that you have some non-perturbative 7-brain structure wrapping a 4 cycle where you realize this SU5, and there are other 7 brains which are intersecting you and producing these matter curves, and there are triple intersection points that give rise to this top Yukawa coupling, in particular to the other ones. Still, even though this non-perturbative built-in structure is able to reproduce the top Yukawa coupling, there is a lot of interest in understanding brain instanton effects in a theory, and for other purposes like SUSY breaking or modular stabilization or neutrino masses or whatever. So this is the interplay, in a sense, between type 2B D7 brain models and F-theory models, and let me just emphasize that in the last couple of years there has been a lot of formal work in matching properties of F-theory, which are coming from different features of the geometry, with properties of 7 brain models, because there is a cell limit where you can kind of bring them together. I mean, there are situations where the matching of these two is applicable, or where you expect that F-theory physics should reduce and reproduce type 2B physics, which in many respects can be very nicely studied with Wolsey techniques, etc. Okay, so let me now move towards a theory and start discussing the most pheno part, which is related, or at least the activity in the last couple of years has been of flavor structures and discussion of unifications. So one of the great things about F-theory is that the Yukawa coupling that gives rise to masses for the fermions is, in a sense, ultra-local. Everything is localized at the point in the internal space. So you can just parameterize the geometry around your neighborhood and just understand properties of the Yukawa couplings, and in particular flavor. So you don't need to understand the whole Calabi-Yau or even the whole cycle, 4 cycle to understand the flavor structures in F-theory, and the E8 point is, in a sense, the ultimate unification from that point of view. So the basic idea is that on each matter curve there are bifundamental fermions which give rise to 4-dimensional chiral fermions because they are living in or coupling to a magnetic field, and they have some kind of Gaussian-like wave function, and the Yukawa coupling is given by just computing the overlap integral of the different zero-mode wave functions. There has been a development in trying to understand in particular this top Yukawa coupling. In the first approximation, or in the first attempts, essentially the main issue is that you get typically an order 1 Yukawa coupling, but the texture of the different families is not correct. You get a rank 1 structure, and the whole battle has been in trying to look for mechanisms to go beyond this rank 1 structure. So it soon became clear by work by Baffa and Cecotti and other people that the work volume fluxes carried on the volumes of these 7 brains cannot deviate from this rank 1 structure, so you must resort into additional mechanism. One of them that they propose is to introduce some bulk fluxes, so 3-form fluxes in the bulk of your base 3-fold, or if you wish 4-form fluxes in F-theory, that would be parameterized as some non-commutative deformation of your work volume theory and your 7-brain structure. Another mechanism is to consider distant instanton effects. You could consider effects of gaugino condensation or Euclidean D3 brain instantons far away from your brains, And when you compute the effect of that on the physics of the Yukawa coupling, you'd see that they also induce some deformation from the rank 1 structure. And in fact, these 2 points of view are actually not different, but they are actually equivalent, and they can be related by the Seiberg-Witten map that undoes this non-commutative structure and essentially maps that deformation to that deformation proposed by Marchesen and Bartucci. This has been the development at the level of computing the Yukawas. Now there are enough ingredients to parameterize suitably the deviation from the rank 1 structure and start trying to reproduce the CKM matrix, etc., etc. Another line of development related to these wave function profiles and their overlap is to compute the effects of Kaluza-Klein modes. In particular, Pablo Cámara, Dudas, and Balti have worked on how these Kaluza-Klein modes would impact typically proton decay or rare processes like flavor changing neutral currents and things like that. Another approach to flavor is the so-called gluing morphism, which essentially amounts to finding a nice mathematical framework to describe how to give vacuum expectation values to fields that live at the intersection. So you can start with some structure of 7 branes which intersect in many ways and find a theory which contains plenty of singlets with respect to the standard model, and the gluing morphism would correspond to a way of giving BEPs to these singlets, and this can be used probably to engineer some kind of Frogat-Nielsen mechanism and perhaps give rise to a theory of flavor within F-theory. So the second aspect in which phenomenological aspects of F-theory have been developed is the issue of unification. So unification was supposed to be one of the great things about these F-theory setups. Now the situation is not as simple. So already in 2008, Blumenhagen realized that because you have some hypercharged flux on your 7-brane warp volume and the SU5 branes to break precisely the SU5, this hypercharged flux distorts, due to some corrections, distorts the naive gauge coupling unification that you get from having some SU5. Now something which is a very nice recent developments by Grimm and collaborators is that they have promoted this computation by Blumenhagen, which was done in the type 2B perspective, just using the Dirac-Bornfeld action for type 2B branes, to rederive the same result using the theory, where essentially it's coming from the effect of the warping induced by G4 flux. So the hypercharged flux in F-theory is geometrized into some larger flux, which is a G4 flux on the Calabi-Yau on some special curves, and because this flux gravitates, it warps your compactification space, and it deforms a little bit the force cycle in such a way that the gauge coupling is effectively changed, and they match precisely the type 2B result in the case where it should, that is in this cell limit in a sense. This lack of unification, that as it was understood before, can be attempted to be fixed with many effects. People have tried using threshold, exotics, many things. And then perhaps one can succeed, although the unification is not as elegant as was expected to be at the beginning. People have looked also at alternatives, like breaking the SU5 not with hypercharged flux, but rather with Wilson lines, that is wrapping your SU5 7 branes on non-simply connected force cycles and turning on Wilson lines as it is done in heterotic. And there were some recent attempts by Rabi, Marzano, and collaborators. Although they were not really successful, they had exotics, but at least the idea was there, and perhaps with a different local geometry they could achieve eventually such an objective. So I would say that in this field of unification in F-theory, the dust is not fully settled, and probably there are more developments in the next year or so. Let me now move towards more formal aspects of F-theory, which are not perhaps motivated directly but by phenomenological applications, but rather they are more motivated by trying to understand better the relation between type 2B and the things that we understand in type 2B models and F-theory. So in the last year or couple of years, they have essentially focused on some issues like understanding the G4 flux that is responsible for the warp volume fluxes on the 7 branes. So not really the bulk fluxes, but rather the ones reproducing the magnetic fields on the 7 branes and thus being responsible for a chirality. And also trying to understand the U-ones in this F-theory compactification. Now, these issues are very sensitive to the global structure of your compactification space, and although there were some early understandings of these issues using the spectral cover, which is a semi-local approach, just describes the geometry close to the SU5 force cycle, the main emphasis has been to understand these issues in the global setup. Essentially, the G4 fluxes are sensitive to the global properties because they must be quantized on any 4 cycle of your compactification space, and the U1s, in particular the massless ones, are sensitive to the global features because they can be broken by any effects coming from some charged particle, which could be a singlet of the SU5, so it could be far away from the SU5 brace, but it still could be charged with respect to this massless U1. So it is important to understand these global issues to address these points with rigor. So the way to do that, to understand in particular the U1s, is to think about M theory on the Calabi-Yau and blowing up its singularities. So there were plenty of works in trying to do that systematically and trying to blow up or studying the blowing up of different codimension, complex codimension 1, 2, and 3 singularities. And essentially they give rise to some cycles on which you can compactify the P forms of M theory to give rise to U1s and study whether these U1s are massless or not. So in particular, there were works by Baegan and collaborators on generating massless U1s by taking Tate models and restricting them so that they are in a particular locus in complex structure moduli space where these U1s are unhiggsed in a sense. Essentially, they correspond to models which have some underlying SU5, which could be broken by hypercharged flux or whatever, times a U1 which remains massless in the theory. The way in which that works essentially is that when you start blowing up your singularities in M theory on the resolved Calabi-Yau fourfold, you find that there are some extra cycles which give you some extra places where you can compactify your M theory three form to get this additional U1 gauge boson. Another important point that they have emphasized is that it is strongly suspected that in these F theory compactifications there are some extra U1s which they call geometrically massive, in the sense that they are there in some suitable sense, although they are not there as massless gauge bosons. In a sense, they would be associated to non-harmonic forms on which you reduce your M theory 3 form, and basically they are associated to possible blow-ups that you can do on your geometry, which are nevertheless non-Keller. Okay, so they violate the Calabi-Yau condition. So they don't really correspond to massless U1s, but you are exciting some massive excitation, right? These geometrically massive U1s are interesting because they are, again, strongly suspected to be associated to the type 2B U1s, which were massive because of the Stuckelberg masses, because of the big wedge F couplings. So it's a nice identification of some perturbative physics of type 2B in this geometric F theory setup. So although the U1s are not there as massless guys, they are there in some sense. And they are important because they could introduce some selection rules and things like that. So the second line of development, which I mentioned, are the fluxes, which are also related to this, because in a sense they are associated to the physics of the of the M theory 3 form. So these fluxes, the fluxes that work has been focusing on, are the ones related to magnetic fields on the 7 brace and are required to reproduce chirality. So one nice development by Grimm and collaborators in the last year is to develop very nice chirality formulas just coming from topological properties of the fluxes. So the strategy is to match the compactification of F theory on a Calabi-Yau fourfold, where you have 4-dimensional chiral fermions, and you reduce that to 3 dimensions, and these fermions will generate some Chern-Simons terms from a 3-dimensional Chern-Simons terms from a one-loop diagram, to match those Chern-Simons terms with the ones that you get at tree level from M theory compactified on this resolved Calabi-Yau fourfold, which already brings you down to 4 dimensions. So doing this matching, this 3-level Kaluza-Klein compactification of M theory in a Calabi-Yau fourfold, you do recover the net chirality, the indices, if you wish, of F theory on the corresponding Calabi-Yau. And the second line of development, which has been relevant, is to match the properties of these fluxes in F theory with properties of the fluxes that people know about in a type 2B. So G4 fluxes on the usual blow-up cycles. The usual blow-up cycles means the ones that you get from blowing up these extra 2 cycles in these restricted Tate models. They correspond to fluxes for the massless U1s. There are also some more exotic fluxes, which are called spectral cover fluxes, uncovered by Marzano, Schaffer-Nameki, and other people, which were identified by Baegan and collaborators as fluxes associated to these geometrically massive U1s. And this is another respect in which these U1s, which are there in perturbative type 2B models, in essence are still there in F theory models. And there is a further class of fluxes which are called, let me just call them non-generic, which are very special. They were described by Colinucci and collaborators, and they are associated to fluxes that rigidify the seven branes. So these are fluxes that make the seven branes supersymmetric only in a particular locus in complex structure moduli space. So they really tend to stabilize the seven branes on that locus. Okay? So there is modular stabilization of complex structure moduli because of the presence of these fluxes on the work volume of these seven branes. And this is something that will come back probably also in the talk by Lara Anderson on the side of the heterotic compactifications on Calabi-Yau. And another aspect of fluxes which has been improved in the last couple of years is the understanding of the quantization of the four-form flux and matching that with the Friedwitten consistency conditions in type 2b. There has been a lot of effort in understanding fundamental aspects of F-theory instantons, in particular Euclidean D3 brane instantons or 3 brane instantons in F-theory. There were some early works on that, essentially by mapping these D3 branes to M5 brane instantons on divisors, so the 6 cycles, which are vertical divisors of some elliptically fiber Calabi-Yau 4 form on the M-theory side. And there is the Witten condition, that the necessary condition for the development of superpotential non-perturbative terms is that the arithmetic genus of the 6 cycles should be equal to 1. Ganor in 1997 already had some understanding about some possible prefactors of these instanton amplitudes, which can depend in general on complex structure moduli and also on brane moduli. In particular, the dependence on brane moduli comes from the fact that there are some, there can be open strings stretching between the Euclidean D3 brane instanton and the 7 branes. That was already put forward in 1997. And another early development, like in 2005 or so, were some partial results of the effect of bulk fluxes in the physics of the zero modes on the instanton and how to lift them. Now, I guess Miriam Svetic will be discussing many of these points, but let me just mention a few developments in the last year or couple of years. So there has been a lot of work in matching the properties of these instantons in F-theory with properties of perturbative D3 brane instantons on the Calabi-Yau orientifold in type 2b by different people, and with what I cannot call other thing but very imaginative techniques like string junctions, anomaly in flow, and using covariant actions on the work volume of the D3 branes. You see, the point is that the D3 brane remains a D3 brane throughout the whole 4 cycle that it is wrapping, but the work volume action that you have is not well defined because it suffers monodromies. So you have to define it by patches, or rather the couplings on your work volume action of the D3 brane are not really functions but are some kind of sections of some SL2 bundle or so. These techniques have been developed and they lead to a very nice matching between properties of M5 brane instantons and D3 brane instantons. In particular, there have been developments about turning on work volume fluxes on your instantons, and this can lead to many interesting effects. For instance, rigidification. So because of the fluxes, your instanton may have some zero modes which are lifted, or even its moduli space may be lifted, because again, as we studied before, you can turn on fluxes that force the instanton to sit at a particular point in its moduli space. Otherwise, it won't be supersymmetric, so it won't be BPS and it won't generate this kind of F terms that one is interested in. And finally, there has been a lot of work about how these instantons violate the U-ones, either the massless U-ones, well, they cannot violate the massless U-ones, but how they violate the geometrically massive U-ones, and what's the structure of charge zero modes responsible for that. And there is a very nice interpretation by Weigand and collaborators related to the Friedwitten anomaly. Basically, the idea is that when you have some D3 brane instanton, it becomes some M5 brane instanton in F-theory, and in the presence of G4 flux, which is always present because of chirality, etc., it will pick up some Friedwitten anomaly. So there will be some uncancelled tadpole on the volume of your M5. So to cancel that tadpole, what you need is to add objects which are ending on your M5 brane, and they will correspond to wrapped M2 branes wrapped on 2 cycles, which are ending on the M5 brane, that will cancel this G4 Friedwitten inconsistency. And the addition of these objects ending in here will correspond to the fact that in a space-time what you have is some instanton, which is the M5, which is emitting some charged particles, which are these M5s. And you can measure the violation of the U-ones that the instanton is putting in by just computing how much the instanton is naively violating this Friedwitten condition, because this is telling you how many extra branes you need to put in and how many particles are emitted in here. Okay. The final aim of understanding all these issues both phenomenological and formal, is to construct models which look like the standard model and to put that together with other ingredients that we know are relevant for reproducing the standard model in string theory, like moduli stabilization. Now, unfortunately, it is very difficult to put forward or to implement in F-theory setup the ingredients that we know are relevant for moduli stabilization. In the type 2b setup, perturbative type 2b, we know that one has to introduce three-form fluxes, instantons, all kinds of corrections like alpha prime or GS corrections, things like that. Now, each one of these ingredients is basically very complicated in F-theory, like three-form fluxes become bulk components of the four-form flux, and they are as hard to be understood as these ones, okay, and they have not been studied systematically. Instantons are under study, but they are complicated, and the corrections are kind of not very meaningful because they are perturbative in a sense, like what's the meaning of a GS correction in F-theory, which incorporates quite a bunch of GS corrections already, and what's the meaning of alpha prime corrections if there are no fundamental strings in F-theory. So many of these issues have to be clarified before one can apply these basic ingredients of moduli stabilization to these F-theory models. So for the moment, most efforts have focused on continuing their study in the type 2b perturbative setup, in a sense. Let me mention that there have been a lot of formal developments about these three-form fluxes and generalizations, for instance, using generalized complex geometry, etc., but these developments, for instance, have not been yet put to use for model building. And similarly, there have been quite some developments in trying to understand these three-form fluxes, particularly by the Munich group, in conformal field theory, just introducing some suitable deformations of the underlying Calabi-Yau CFT, in a sense. But again, they are not yet ready for application to model building. So the developments have gone in the different directions. First, there have been developments in the so-called large volume scenario, where you pick some particular classes of Calabi-Yaus, which they call a Swiss cheese, because they have some structure of 4 cycles where there is a large one describing the overall size, and there are some smaller ones which describe the holes in this Calabi-Yau. And on this compactification, you essentially put some fluxes to stabilize complex structure moduli, also possibly some brain moduli. And you put some instanton or non-perturbative corrections, and also some alpha prime corrections, which are basically arising from the R to the 4 term in 10 dimensions compactified down to 4 dimensions. And sometimes they also put loop corrections. So it's a complicated setup with many ingredients all put together. The developments have been essentially in trying to develop a systematic search for Swiss cheese Calabi-Yaus using polytopes and toric methods. The criteria they are imposing is that they have not only the appropriate intersection numbers and a structure of 4 cycles, but also that they have actual cycles to support the instantons and the standard model ingredients that are actually invoked in this moduli stabilization. Another line of development in this project of moduli stabilization and de Sitter is to study the uplift by introducing localized sources. This is inspired by the KKLT scenario, where you put some anti-branes whose only role essentially is to uplift a little bit the vacuum energy of your compactification, which at the earlier level is just anti-de Sitter. There have been some explorations, and there is some controversy about the effect of the back reaction of these anti-D3 branes. So this is a point where probably further work is needed and further understanding is needed to pin it down. But let me just emphasize that there has also been some work on alternatives to introducing anti-D3 branes. And there is a work by Quevedo and other people just this year, where essentially they obtain the uplift term by using non-perturbative effects that, rather than depending on the T modulus, that is scalar moduli, depend on the dilaton. Now, since the dilaton is supposed to be stabilized by the three-form fluxes, it can be treated basically as a constant, so the non-perturbative effects correspond as some uplift term. And something which is nice is that they observe that this new ingredient kind of mimics very well what an anti-D3 brane is doing, and probably what is going on, although it has not been worked out, is that there is a geometric transition that geometrizes this non-perturbative effect into some flux or deformation of the background, which is very similar to the one which would be created by anti-D3 branes. On a different line, but again in this project of trying to understand the de Sitter spaces in string theory, let me mention this work by McAllister and collaborators, where they took a completely different approach, which is more like a statistical, just looking at the landscape of flux compactifications. And the way to do that is to think about the effective supergravity theory with the Geller potential and superpotential regarded as random functions. And they proposed a matrix model that would mimic the distribution of vacua in that situation. They could compute things like the distribution of things around or the distribution of the cosmological constant around 0. And they suggested, or the matrix models that they were using suggested, that there is some exponential suppression of the Sitter spaces, just because typically these random supergravity theories produce tachyons, that is, they produce instabilities which are not worrisome in the anti-de Sitter setup, but they would lead to instabilities when you uplift. So to really obtain something which is stable de Sitter, what you need is to have all your mass squares to be positive, and that's regarded as a fluctuation because the average is to have tachyonic degrees of freedom, and to really generate a de Sitter you need that each and every one of the modulus that would have a tachyon really suffers a fluctuation towards positive mass square, and because of eigenvalue repulsion they say that this is exponentially suppressed. So this is an interesting piece of work, and probably has some impact on our view of the landscape, and in particular the de Sitter landscape, at least within this restricted setup with some assumptions. Let me now leave these type 2B and F-theory compactifications and say a few words about heterotic theories. Let me just mention that most efforts about the heterotic are in the model building side, I will say, and a little bit on the modular stabilization side, but not in precisely the same way as in here, basically because fluxes are hard to understand in the heterotic, and a lot of formal work is undergoing to understand fluxes and geometric fluxes, etc., and non-Kähler spaces in heterotic compactification. So I guess Lara Anderson will be discussing about that, but let me just point out two recent developments in the heterotic side, I mean heterotic compactified on smooth Calabi spaces. There has been a lot of progress in understanding construction of stable bundles based on line bundles, and there has been a construction of several hundred new MSSM-like models by Lara and collaborators. Essentially, introducing line bundles correspond to just what we would call magnetization of branes in the type 2B or F-theory setups. So the basic idea is start with the E8 times E8 and introduce a bunch of line bundles rather than some SU5 bundle, and you introduce a U1 to the 4 bundle that breaks down to SU5 times U1 4, that would be the 4-dimensional gauge group. You do Wilson line breaking of the SU5, and you do something about the U1s. They could be broken by singlet BEPs, or they could be broken by other things, or they could remain massless. Typically they will be anomalous, and they will be made massive by BF couplings, exactly in the same way, in a sense, as we saw for brane models. Now, something which is interesting is that these people have enough knowledge about the models to really compute what are the allowed superpotential couplings, and again, these U1s impose a lot of selection rules. So to really obtain some interesting superpotential textures, like to explain Yukawa couplings, etc., essentially what you do is, these features improve a lot if you break some of the U1s, and the simplest way to break them, perhaps, is to break them by using the Wilson lines that already break the SU5. So essentially what you do is when you go around the non-trivial cycle in the Calabi-Yau, you exchange some of the U1s so that some of them, the off-diagonal component or the antisymmetric component is broken, and the final model has less U1s, and there are less selection rules consequently. So this story is very reminiscent and probably very similar, and perhaps even dual, to the F-theory monodromies that were studied in the spectral cover approach, where you start with a structure with SU5 times U1 to the 4, but then you kind of mix together the different U1s to have a less U1s and less selection rules, in a sense, and have improved the superpotential textures. So the progress here has been to the systematic construction of MSSN-like models, which has so far produced several hundred models, although I think they have the potential to construct many more. So they have some talk by Andrew Lucas. He was saying that they are ready for mass production of MSSM-like models in this setup. Another piece of beautiful work that they have been working on, I mean Lara Anderson and collaborators, is the stabilization of geometric moduli from the bundled SUSY conditions. So this is the heterotic version of the earlier F and D terms on branes. Essentially what you have is that the SUSY conditions on your branes, in this case on your bundles, involves a condition on the Kähler moduli and on the complex structure moduli, so that the branes are supersymmetric only on some special locus or loci of your moduli space for Kähler and complex structure moduli. So this was already done in a sense in the 2005s by Antoniades and collaborators in the case of D branes in toroidal setups and toroidal orbifolds and orientifolds. what Lara and collaborators have achieved is a powerful mathematical description of this complex structure moduli stabilization, which is related to this Atiyah class, and they construct models where many and most moduli are stabilized. Now, the question in heterotic is what happens with the leftover moduli and how to do the uplifting, which is a much harder question that probably they will address in the future. There has been other lines of progress in heterotic orbifolds, mainly not perhaps so much on the construction of new models, because there were already large classes of models by Niels, Ravi, Ratz, and collaborators, which they call the mini landscape models. So essentially, most analyses have been developed to understanding further properties of these models, and they go into different directions, like understanding or developing computational tools to compute the D and F flat directions, which are required to be taken to restabilize the models at one loop because of the anomalous Fayet-Dilopoulos term for the U1, which in this case, and contrary to the D-brane setup, is controlled by the dilaton. And beyond these computational tools, they are interested in what kind of interesting features you have once you take these flat directions, and in particular, how to preserve discrete symmetries and things like that. Finally, there have been developments on other CFT models, both in heterotic and other models. Let me just recall that in the context of intersecting branes or magnetized branes, there was a huge class of models developed by Selekens and collaborators based on Gepner orientifolds, where different boundary states play the role of intersecting branes. This has been testing ground for many ideas, and now this story, which got kind of started in the D-brane side, has moved towards the heterotic side, and Selekens and collaborators have developed a lot of MSSM-like models based on heterotic on Gepner models, so old-fashioned technology, but with a new twist, which they call heterotic weightlifting. Okay, that's all very nice, but I guess when you go back home and you're with your friends and in dinner or in the coffee table, they will ask you, well, these things you're working on, are they related to the Higgs in some way? So are you working on these Higgs? Well, the simple answer is no, but there may be more complicated answers, so let me spend a few minutes on that. So in the last year or couple of years, there has been some interest in string phenomenologists to really bring down all these formal technological tools to understanding some real physics, in particular the Higgs. So before, the emphasis was to understand the soft terms and the SUSY spectrum, but SUSY is becoming less fashionable and Higgs has become much more fashionable. So the focus has moved towards the Higgs. And there are several scenarios which explain or reproduce the right Higgs mass. Okay. Of course, they are under certain assumptions on moduli stabilization and SUSY breaking source. So you parameterize these ingredients because you don't know how to work with them in full detail. So you parameterize them in terms of a few parameters, and then you use some inputs, which could be the dark matter relic density or solving the cosmological moduli problem or bounds on rare processes or whatever, to put constraints on these few parameters. And then you can, in that particular setup, a restricted scenario, ask the question of what happens with the Higgs mass. Okay? So there are many ways of doing that, so you cannot, I think it is too strong claim to say that there are predictions for the Higgs mass coming from a string theory. But on the other hand, you can turn this kind of prediction around and say that the Higgs mass carries a lot of information about the high energy physics. And in particular, it points towards several high energy scenarios. So let me just mention a 3-line lesson that you can take home and discuss with your friends over coffee or dinner table or whatever. The first line is that the questions on the Higgs sector can be addressed in a string theory in this restricted setup, but you don't need to say that to your friends. There are several general plausible scenarios. Plausible in the sense that there are underlying ingredients that we understand very well microscopically, although it's hard to put all of them together, but we can parameterize them. And something which is nice is that the different scenarios are not all identical. They may all give the right Higgs mass because we have just measured it, and then it's nice to get a number, but they differ in the other predictions for the LHC. Okay, so they are testable, and in a few years we will know which one of them are incorrect and whether all of them are incorrect. A 4th-line lesson is that there is life apart from the Higgs, although it's not so obvious these days, and there are other possible predictions of string theory for the TeV scale. So let me illustrate some of these constructions or scenarios for the Higgs mass and describe 2 takes on the Higgs mass coming from the type 2b side, and I will tell you what are the assumptions, and then you can judge for yourselves. Okay? So let me try to give you some flavor on this, and let me start with type 2b or F-theory compactifications with 7 branes, and I will not do that. I mean, this is based on work by Ibanez and collaborators, which is the one I know most and I will describe. Let us break supersymmetry and stabilize moduli and forget about those issues by putting some 3-4 fluxes for which one can compute quite explicitly what are the soft terms, assuming that one has some MSSM construction. So the soft terms look like something like that, and you don't get the 100 and whatever parameters of the MSSM, but rather you have just one parameter which is an overall scale, and all soft terms are related to that. The overall scale can be computed in terms of the compactification scale, the Planck mass, and then some perhaps suppression factor, which I put there for convenience, which is related to how much the fluxes may be depleted or increased nearby your branes. Now, let me start with the first scenario, which is kind of a standard with low energy TeV scale SUSY breaking. This is work done by Aparicio, Cerdeño, and Ibanez throughout the last couple of years. So you engineer TeV soft terms by taking the compactification scale to be 10 to the 11 GeV, or if you wish, taking the compactification scale to be around the GUT scale and then putting some suppression, because otherwise this would be too large. Then what you get essentially, or what they propose, is a 3-parameter model, which is this overall scale here for all these soft terms, the mu parameter, for which they didn't have any greater idea than putting it by hand, and then some kind of correction of this universality of the fluxes coming from some work volume fluxes or whatever. Now, they have these 3 parameters and they impose 2 conditions. The first is to have radiative electroweak symmetry breaking, so that when you run down the soft terms of the Higgs, you find some unstable situation and then you have electroweak symmetry breaking. And they require that the neutralinos provide a dark matter with the appropriate relic density. So they have essentially 1 parameter left because they have these 2 conditions. So they use some strange or rare decay of the BS, and essentially they were able to put bounds on this parameter M, which is essentially this particle masses, which should be pretty large. And then, because you're pushed down to this regime, you can compute what's the Higgs mass in here, which is 125. Okay? Let me say that this is not a univocous prediction. So in particular, something that they emphasize is that if the bounds on this decay increase, you will be forced to even lighter Higgses, so the model will be ruled out. So it's something which is testable. Okay? And again, as I was saying, the predictions, there are other predictions for the LHC physics. In particular, this one would predict that these particles are pretty heavy around this range mass, but some of them would be accessible for LHC at 14 TeV. There is another scenario, again proposed by Ibanez and other people, which is more speculative if you wish. It's based on taking the soft term scale to be intermediate scale. So below that, what you have is just the naked, bare, non-supersymmetric standard model. You choose the compactification scale to be around the GUT scale, and then the SUSY scale, SUSY breaking scale is the intermediate scale. There are many issues you have to deal with or not deal with, like the hierarchy, which you just fine-tune. You don't invoke supersymmetry to solve it. There is non-supersymmetric unification, precisely using the F-theory corrections that were discovered by Blumenhagen. You have to worry about dimension 6 proton decay, etc., etc. But the key point is that if you engineer in some way that the quartic coupling of the Higgs is vanishing at the SUSY breaking scale by some symmetry or whatever, and Hebecker and Weigand proposed mechanism to do that, then you reproduce a 25 GeV, 125 GeV Higgs. So let me move to conclusions. Something that I like to emphasize is that it's always surprising and amazing that something close to the standard model can be realized in string theory, because it was not devised to do that. There is continuous progress along different lines, and things are getting closer to particle physics phenomenology at the LHC, because we are getting to this data-driven era where we have to worry about this. There is a lot of room for improvement in this LHC era, and if you're interested in moving towards this field, let me just emphasize that there are some good opportunities by advertising this meeting that we will have in Madrid in September, and also by taking the opportunity to advertise our book, which is just appeared and is there in the Cambridge University Press stand. Thank you.
Thank you very much. So are there questions or comments? Oh, yes.
Can you comment on the status of supersymmetry breaking?
The what?
Status of supersymmetry breaking.
There are several scenarios. The main one, I would say, is using fluxes. which is kind of a 3-level scenario. There have not been so many developments because most of the impact of those non-supersymmetric fluxes on brains were already computed, so you have an idea of what are the soft breaking terms that you get. Typically, they correspond to gravity mediation. The other scenario that has been used is not as precise, it's more like string inspired, is using just non-perturbative effects in a very generic way, so you just propose a superpotential that depends on all moduli, and then you find that the typical minima is non-supersymmetric. But it relies heavily on just using instanton effects for everything, modular stabilization and Susy breaking, and because we know so little about them, it's very hard to make this scenario quantitative, I would say. They have very different signatures. For instance, if you do everything with non-perturbative effects, typically you have a lot of actions moving around, whereas if you stabilize with fluxes and break Susy with fluxes, typically the actions are eaten up by Stuckelberg mechanisms and things like that, so they disappear. So they are pretty different and they have distinct features at low energies.
More questions?
It's more a comment. There are other ways to get a 125 GeV Higgs rather than tuning all those super partners to be very heavy. You can also imagine additional states which mix with the Higgs. And there are various scenarios for doing that in strings. For example, extra sectors which couple to the standard model. Anyway, so you don't have to. The other thing was a question about in light of recent updates on bounds on neutralino dark matter, how much of the parameter space that you were talking about for these flux moduli stabilization scenarios is still left over?
Yeah, well, neutralino dark matter is kind of the standard paradigm, although it relies on Susy, which is the standard paradigm, and these things are becoming perhaps less fashionable, although it's still the preferred scenario. Of course, you have to fine-tune into the coannihilation region and things like that to really get the appropriate relic density. So this is the well-tempered neutralino of Judith and collaborators. This can be done. I mean, particularly in the first scenario for the Higgs that I was discussing, it's something that they impose, that they get the appropriate neutralino relic density to explain the dark matter. So it can be accommodated, although in that scenario you didn't have a natural explanation for sitting precisely on that corner. In string theory, there are also alternatives. Another alternative, which would be realized in the second scenario, would be to have actions as dark matter. But that depends a lot on your scenario for actions, which, as I was just mentioning, depends a lot on what you think about modular stabilization and Susy breaking, and whether there will be actions around after Susy breaking because you stabilize with non-perturbative effects, or whether you stabilize with fluxes and most of them are eaten up. But of course, the question of actions is also related to the Pechi-Quinn action, I mean the QCD action, and that's a tough issue. I would say that there is no fully convincing realization of the Pechi-Quinn QCD action in string theory as yet.